Okay, let's get started. I think some of you you can see me, I assume, and assume you can see them as well. Is everything okay? Can you guys see it okay?
Yeah, just give them a minute or so.
So, okay, can you hear me or not?
Yeah, the audio is pretty clear.
Okay, so I apologize for this problem, but you can blame the TA. I tried everything I can to solve this. But okay, I'm recording the lecture, and Naren, you should go get your laptop so we can project it.
Sure, yeah.
So go do that right now. So today, so the slide should be here. So today our goal is to go through the basics of solar radiation. But before we do that, I also want to make a couple of announcements. First, I haven't finalized the teams yet. So I know some of you have emailed me, but if you have some suggestions for preferences for your projects, make sure you send me an email by today. I'll finalize the teams tomorrow in tomorrow's class. Now, tomorrow's class, this problem should not exist because we'll be back in our correct classroom. So hopefully it should be okay. Okay, before I start, are there any questions?
No.
Okay, so I guess let's begin. So the goal today is to get a basic understanding of sunlight and particularly about how to do the measurements for sunlight. So solar radiation is a source of all of Earth's energy, everything from heat to food. Fossil fuels can be thought of as stored solar energy for millions of years ago, so it's pretty obvious. Biomass converts solar energy to fuel. So biomass is the most prevalent form of source of energy, particularly in the developing world, where essentially biomass refers to wood and dried carbon contents that can be converted directly. That's basically solar energy, which is converted and can be used for fuel. Wind, of course, is the result of motion of air, and the motion of air comes from heating from the sun. So and also its rotations. So in a sense, wind energy is a result of solar energy as well. Finally, hydropower is generated by the sun, since the evaporated water returns to Earth as rain and fills the dam. So everything kind of, in a sense, except nuclear power, can be related back to sunlight. So which is why it's important for us to understand what sunlight is and how to do the measurement. So let's begin with some very basic ideas of light, which some of you should be quite familiar with, but let's go through it anyway. Light, of course, comes in many wavelengths, which we refer to as the electromagnetic spectrum. We think about the spectrum in terms of wavelengths. So wavelength is shown here. It can range anything from, this is a meter, so this is a kilometer of wavelength, that's a radio wave, down to, let's say, a centimeter in wavelength, a microwave, down to, let's say, a micron in wavelength, the infrared, and about a few hundred nanometers, it's the visible, and shorter than that, you have the ultraviolet, X-ray, and gamma rays, and so on. So this shows roughly the wavelength of light, and as you can see, as you decrease the wavelength, the wavelength gets bunched together, and this is an important idea we will have to come back to. Now, wavelength is of course related to frequency, which is plotted here, where frequency is inversely proportional to wavelength. So as the wavelength decreases from left to right, the frequency increases from left to right. And this is the frequency corresponding to these spectral components. And if you look only at the visible component, if you blow it up, this is what you see. And you can clearly see that the red light has longer wavelength than the violet, but red light has smaller frequency than the violet. And this is, of course, as we see in rainbows and so on. Now, why do we need to understand this? We need to understand this because, remember, we are interested in converting sunlight into energy. So we need to understand how much energy or power is in sunlight. And the way to think about it is by this very simple equation. E, which is the energy of one photon of light, is h, which is Planck's constant, multiplied by frequency nu. Okay. Now, what we have learned in undergraduate physics, in first year physics classes, is that light exists as a wave which means we have wavelength and frequency, but it also is a particle, which means that it has momentum and energy. Okay, so it is essentially kind of have this duality between a wave and a particle. And the energy of this photon, which is a single particle that represents light, is h times nu. Now, the frequency nu is related to wavelength by c over lambda. So nu, the frequency, is inversely proportional to lambda, which is the wavelength, to the constant c, which is the speed of light. Now, characteristics of light that are relevant to energy, which is what we're interested in, is number one, is the spectral content of the incident light. So it matters what the color of the light is. It determines how much energy there is for us to grab. Number two is the radiant power density of the sunlight. In other words, how much power is there per unit area. So the concentration of energy is the way to think about it. And that becomes very important when we talk about solar concentrators. Number three is the angle at which the incident sunlight strikes the absorber. So typically when you try to convert sunlight, you need to have something that absorbs light, which could be a solar thermal device, or it could be a photovoltaic device. And the angle at which it's incident determines its efficiency, in a sense. And we'll also think about that. Of course, because we're interested in a long-term usage of solar energy, the energy from the sun as it varies throughout the year, through the seasons, is also important when we try to design systems. So we need to keep that in mind as well. Okay, now let's think about some of the basic properties of light in some more detail. So the energy of, so a beam of light, whether it's coming from the sun or a flashlight or a laser, can be thought of essentially like a flow of little particles. And these particles are called photons, okay? And the energy of each photon is h times nu, hc by lambda, where h is the Planck's constant, which is roughly in the order of 10 raised to minus 34 joules seconds. That's the unit. We can also express, because these are very small numbers, we can also express the energy in electron volts, or EV, where 1 electron volt is the energy required to raise an electron through 1 volt potential, which means that if you had 1 electron and you accelerate it by applying a potential difference of 1 volt, the amount of energy gained by that electron is 1 electron volt. And 1 electron volt is simply, it's just essentially the charge of the electron multiplied by 1 volt, and the charge of an electron, as you may remember from your physics classes, 1.6 times 10 raised to minus 19. When you multiply by a volt, you get a joule. Okay, so that's 1 electron volt. Okay, now let's do some practice, and you can discuss among yourselves, just the students who are there. What is the energy of a green photon? The wavelength is 500 nanometers. I want you to think about this for a second, how to do it, and just approximately estimate. Okay, I'm not sure. That's better. This, do you guys know? I can see you, so you can discuss. And what is the energy of a green photon?
Just the constant multiplied by the speed of light divided by 500 nanometers.
Yeah, so approximately estimated in joules.
We can see the constant is 6.6, but
10 raised to minus 34.
there's okay.
So just an order of magnitude is fine. So you can see it's 10 raised to minus 34 multiplied by, what's the speed of light? 10 raised to 8 meters per second divided by 10 raised to minus 9, let's say, 10 raised to minus 7, let's say. Do you guys follow? So 10 raised to minus 34 times 10 raised to 8 gives you 10 raised to minus 26. And divided by 10 raised to minus 7.
Negative 19.
10 to minus 19, yes, that's correct. So it's about 1 eV, let's say, a little bit more than an eV. Actually, yeah, slightly more than 1 eV. Okay? Does everyone see that? Okay, now the next question is, what is the energy of an infrared photon? The wavelength is 1 micrometer.
To the negative 20. Right?
So compare it to the green photon. What is the difference in energy? So how much more or less energetic is the infrared photon compared to the green photon?
Less energy, like 10.
Yeah. By how much?
10. I mean,
Well, you can look at the wavelength, right? So the wavelength is twice as high.
but the energy is
So for the energy should be?
less.
It should be half, right? Because it's inversely proportional to lambda, and if lambda is 2 times, the energy must be half. Do you see that? So the energy of an infrared photon is half that of a green photon. Okay? Now, this is the reason why it's very important to understand what the color of light is, because the photons of different colors obviously have different energy and can have a pretty big impact. Okay? The next concept we need to understand is what's referred to as the photon flux. The photon flux is defined as the number of photons per second per unit area. So flux always refers to the number of particles per second per unit area. This determines the number of electrons generated in a solar cell, for instance. So in other words, one photon can give rise to one electron hole pair or one electron, which goes into the battery. Okay? So the number of photons is very important to determine the current out of solar cells, for example. And the number of photons is a different concept than the energy of the photon. So the flux itself can be defined as the number of photons divided by time divided by area. And its units, of course, is per second per meter squared. Okay.
Like the color of the photon, is it more darker, has more energy, right? Because the green is darker than red.
So you should look at the wavelength. So it depends on the wavelength.
So the wavelength,
if you have more energy in the longer wavelengths, more particles, more photons in the longer wavelengths, you have less energy, right? It's inversely proportional. So the red photons have less energy than the blue photons. Okay, does that make sense? Let's keep going, and then you can think about some of the concepts as we go along. But so we talked about energy and we talked about flux, but flux and energy are somewhat independent. In other words, the photon flux doesn't give any information on the photon energy. So you can have a flux for blue photons or you can have a flux for green photons, and they could mean completely different things in terms of energy. So in order to compute power density, we need to multiply the photon flux by the energy of a single photon. So the H, which is the power density, which is energy per time per unit area, which is watts per meter squared, equals the photon flux, phi, which is the number of photons per unit area per second, multiplied by the energy of one photon, hc over lambda. Okay, so that is the important quantity when we're trying to get how much energy is coming into the system, for example, from the sun. And keep in mind that this is wavelength dependent. Okay, now let's do a few more example problems, actually, so to clarify this point. So if a red beam has the same power density as a blue beam, which beam has a higher photon flux? So I want you guys to think about this for a couple of minutes. And again, in this class, it's quite important that you have some intuitive feel for what these things mean. Okay? And you can discuss.
The red beam has a higher wavelength, and that's the universe proportional to the density. So the green photon has higher density. Oh, if the beam has the same density, which yeah, the green one, the red one, because the red photon has a higher wavelength. The red
Right.
one.
So let's think about how to solve it. If the red beam has the same power density as a blue beam, which beam has a higher photon flux? So power density is the photon flux multiplied by the energy of the photon. So the question we need to answer is, what is the energy of the red photon compared to the blue photon? So the red has lower energy than the blue photon. So you need more of it to keep the same power density. So you have the red has a higher photon flux than the blue. Okay, is that clear? So then let's think about the next question. If both the red beam and the blue beam are incident on a solar cell, which will produce higher current? That's the first part of the question. Let's think about this.
I mean, if you have a higher flux, then the current is more like flux multiplied by the area. That's the current.
That's correct. Exactly. So the one that has higher photon flux will have higher current. Exactly. So in this example is what? Red. Exactly. So think about it this way. Imagine you have a red laser and a blue laser pointing at a solar cell, and you ensure that the power density of both those beams are exactly the same. You should expect, everything else being equal, the same current to come out of the solar cell, because each photon, not the same current, the red to produce more current than the blue, just because you have higher number of particles from the red going into the cell. Now, of course, there is one very important caveat here, is that the red has enough energy to essentially create the electron hole pairs in the solar cell. We're going to make that assumption in this case. And we'll go back to that physics later on in the semester. Now, let's ask the last question. Which will produce more electric power?
P equals IV or I squared multiplied by resistance. if you have a higher current, then you have, if you have the same voltage or same resistance, then you will have a higher power.
Okay, what do you guys think?
Oh, same power principle. Yeah, it's gonna be the same.
Right, exactly. So remember, even though your input power is exactly the same, right? Power density is the same, assuming it's the same area solar cell. Power density multiplied by area is the total power. So the power is the same in both situations. So one would assume that the cell will produce the same power in both cases, but the simplifying assumption is that the efficiency of the solar cell in both cases is the same for the different wavelengths. That's in generally not true, but we're going to make the assumption for simplicity here. Okay, so this is why it's quite important to have a good understanding of what wavelength is, what power density is, what flux is. Okay, intuitive understanding. Okay, let's keep going. So coming back to the basic properties of light, spectral irradiance is another very important property of any source. And spectral irradiance is simply the power density as a function of wavelength. This is the most common way to characterize the source, and these are example spectral irradiance from various sources. So you can see the blue curve for the halogen lamp. This is wavelength, and this is spectral irradiance, and the units you can see are, in this case, microwatts, but let's say watts per meter squared per micrometer. Okay, so this is power density, which is watts per meter squared per wavelength per micrometer. Okay, so in other words, this number here at 300, if you look at this curve for sunlight, solar irradiance, it'll give me this number. Let's say it's about 7. That's 7 microwatts per meter squared at this particular wavelength. Okay, and F, which is the spectral irradiance, is simply the total power density divided by the wavelength. Now, if you have a continuously varying source like this, you have to take a derivative. You take the derivative of the spectral power density divided by d lambda. And you can show, based on that, this is the flux multiplied by hc over lambda squared. Okay, so that's the spectral irradiance. This is the flux, and hc over lambda is the energy. So spectral irradiance is power density per wavelength. Flux is the number of particles per unit area, per unit time. And this is the hc over lambda is simply the energy of each photon. And we'll keep coming back to this because it's an important concept. Now, the next thing to understand is from spectral irradiance, we can calculate what's called the radiant power density. This is the total power density coming from the source. So it's the total power density emitted from a light source, and it can be calculated by integrating the spectral irradiance over all the wavelengths of interest. So H is simply the integral of the spectral irradiance over all the wavelengths from 0 to infinity. Okay. Now, let's ask what are the units of H. I want you guys to think about that for a second. So previously we said F is H over lambda, or phi hc over lambda squared, and H is the integral of F d lambda. So what are the units of H? And you can think about this.
F times lambda.
Yes, so what are the units of F? F is spectral irradiance.
Microwatt meter square. That's it.
Right, because F of lambda is watts per meter squared per micron or per wavelength, and you multiply it by the wavelength, so this becomes watts per meter squared. Okay, so radiant power density, as you expect, is watts per meter squared. And that's exactly what you expect, right? It's power density, power per unit area. Now, in most cases, like in these kinds of spectra, this computation has to be done numerically, and there are many different ways to do it, but instead of doing an integral based on a continuous function like this, you end up doing a computation like that, where you add up h of I, delta lambda, f of lambda I, and then you numerically add them up. And there are, of course, many ways to do this in MATLAB or whatever. You can do numerical integration. Okay. Now that we have some understanding of some of those basic concepts, we need to think about how to describe the distributions or generalize the description of the spectral irradiance distributions. So this is based on what's an idea called the blackbody radiation. The light sources such as the sun, incandescent lamps, and almost all sources, including lasers, can be modeled as blackbody emitters. Actually, not lasers, sorry, that's strong. All incoherent sources. An ideal blackbody essentially absorbs all radiation incident on its surface and emits based upon its temperature. Okay, that's the definition of a blackbody. It'll absorb everything, but its emission depends upon its temperature. The spectral irradiance of a blackbody is governed by Planck's radiation law. Again, you don't need to memorize this, but that's what it is. Essentially, the spectral irradiance against the power density per unit wavelength is given by this equation. Of course, it depends on the temperature shown here. T is the temperature of the blackbody. That's the most important thing here, and the wavelength. But we'll come back to that. Now, the total power density, which is the total radiant power from the source, of course, as we saw in the last slide, is the integral from 0 to infinity of f of lambda d lambda. And if you do this integral, this is analytical, you can actually do this integral yourself because it's integrating from 0 to infinity. You'll end up with a very simple expression that h is equal to some constant sigma times the fourth power of the temperature. And this is referred to the Stefan-Boltzmann law. And all it means is that the total power density of a blackbody is directly proportional to the fourth power of the temperature of the blackbody. Sigma is what's called the Stefan-Boltzmann constant, and it is 5.67 times 10 raised to minus 8, and its units are joules per second per meter squared per Kelvin raised to 4. And you can check the dimensionality here. Joules per second is watts, watts per meter squared is power density, per Kelvin raised to 4. So if you multiply it by Kelvin raised to 4, you get watts per meter squared, which is the units on the left-hand side.
So from this equation, I'm assuming the total power density will be the same. It doesn't matter what's the wavelengths of the lights.
That's correct, because this is integrated over all the wavelengths. Exactly right. Okay. However, if you are a solar cell and you're trying to absorb this energy, the wavelength distribution is very important. It's not the total power, because not all wavelengths can be absorbed by the solar cell equally. Some wavelengths can be absorbed more efficiently than others, and we'll talk about this later on. But for now, you're correct. And also you can look at these curves, which is basically the, sorry, let me go back. These are example blackbody curves at different temperatures. So you can see 3000 Kelvin has this curve, 4000 Kelvin has this curve, maybe 5000 Kelvin is that, and this is 6000 Kelvin is that. So you can see the total, this is intensity, by the way, this is wavelength. As the temperature increases, clearly the total power density also increases, which is the area under this curve. Now, you will also notice something very interesting. This curve, this dashed line here is plotting the peak of the blackbody radiation, peak intensity, as a function of temperature. So at low temperature, the wavelength, peak wavelength is here. At higher temperature, the peak wavelength shifts down, it's down and so on, and you get this curve. Okay, and that's the subject of the next slide. Another important parameter is the wavelength, or the spectral irradiance is maximum. That's the peak wavelength. And if the spectral irradiance is given by Planck's law here, you can find its maximum by simply taking the derivative with respect to wavelength and setting it to 0. We've done that here. And that peak wavelength is now given by this very simple equation. If you actually do this integral, it's 2900 divided by T in Kelvin. And this can be called the Wien's law. Okay. So basically what this is saying is that the temperature of the black body affects both the spectral distribution as well as the total power density emitted. Okay. So the temperature not only determines the distribution of light, and you can clearly see that here, right? This is very, very flat, whereas at high temperature this is very narrower. But it also changes in the peak. The amount of energy also goes up. The total power density also goes up. So let's do a simple example. This is an example of an astronomical image from the Orion constellation. And if you just look at these two stars here, Rigel and Betelgeuse, which star is hotter? I want you to think about this for a few minutes. Oops. So, what do you think?
Blue one's hotter.
The blue one's hotter, yes. Why?
Because blue one has shorter wavelengths.
Right, so you can think about the lambda peak being blue here, whereas it's red here. So of course, the red is longer than the blue, which means that its temperature has to be cooler than the blue. They're inversely related. Okay, so that gives you a way to think about black bodies as well. Now, the particular black body we're interested in, of course, is the sun. The sun is very complicated, but you can imagine it basically as a hot sphere where there are many nuclear reactions going on in its core, which essentially convert hydrogen to helium. And the internal temperature, because of the energy released during this nuclear reaction, can reach over 20 million Kelvin. Okay, but on a more detailed level, the sun essentially has many layers. So you basically have the core where most of the nuclear reaction happens. So lots of energy is generated. There's a radiative zone, convection zone, where all this energy is propagating outward, and then by both radiation and convection. And it ends up being the surface where there's a plasma, and it's called the photosphere. And that's the temperature we will use for blackbody radiation, as we will see. So the inner core is where you have hydrogen becoming helium, and the temperature is over 20 million Kelvin. Radiation from the inner core is absorbed by the hydrogen ions closer to the surface by both convection and radiation. The sun's surface, which is basically a plasma of ions, is also called the photosphere. The temperature is about 6,000 Kelvin. Okay, and we, for all purposes, will treat the sun as a black body with a temperature of 6,000 Kelvin for simplicity. So if you look, what is the peak wavelength of radiation? You can go back to, of course, you can calculate it from the Wien's law. So it's 2,900 divided by 6,000. It's roughly half micrometers. Okay, it's half a micrometer, and you can see it in this curve as well, which turns out to be in the order of yellow. Okay, this color, do you guys see that? So the peak wavelength from the sun is around yellow, greenish yellow. Oops, that's loud. Okay. Now, whoops, let me head back here. The solar spectral radiance resembles a black body at 6,000 Kelvin, and you can compute the total power emitted by the sun by the power density multiplied by the surface area of the sun, and it turns out to be about 9.5 times 10 to the 25 watts. So that's quite a lot of energy, obviously. Okay. So here's the detailed solar radiation spectrum, where the x-axis is the wavelength, and the y-axis is the spectral irradiance. Just like before, it's in watts per meter squared per nanometer of wavelength. And you will notice first the wavelengths in nanometers going from the UV, which is a few hundred nanometers, all the way into the visible infrared, over 1,000 nanometers is the near infrared, and the mid infrared, and finally, mostly the mid infrared. Okay, so the gray curve here is the 50 degrees, so close to 6,000 blackbody spectrum. In fact, the 6,000 will be slightly higher. Now, the yellow plots here, which have these very sharp variations, is the sunlight at the top of the atmosphere. You see these very sharp variations because there are absorbing ions which exist in the sun's atmosphere, photosphere, which affect some of these essentially resonant beats. Okay, so this is what the radiation you'll see right outside the Earth's atmosphere in space. And the red curve here is what you will see on Earth, on the surface of Earth. So, for example, if you are trying to design a solar system for performance on Earth, you would use the red spectrum. Whereas if you're trying to design a solar system for performance on a satellite, you would use the yellow spectrum. And they're quite different, as you can see. The difference between the yellow and the red primarily has to do with absorption within the atmosphere. And we'll talk about that next, but you see these very sharp dips here. This is oxygen absorption. This is a water absorption. This is another water absorption, another water absorption. Here's some CO2 absorptions and so on. Okay, so that's the basic idea. So, solar radiation in space. So how do you estimate solar irradiance at different distances from the sun? In general, the solar irradiance on an object some distance d from the sun is found by dividing the total power emitted from the sun by the surface area over which the light falls. Okay, so you can imagine the sun being a ball, a point source, and light is going in all directions, and it is spread over essentially a sphere of increasing diameter. Okay, so if I think about H as the power density at some distance away from the sun, I can compute that by looking at sigma T raised to 4 from the Stefan Boltzmann law, multiplied by how much the energy has spread. So 4 pi r sun squared, which is the radius of the sun, that is the irradiant power density right outside the sun's photosphere, and I divide it by the distance I moved away from the sun, which is 4 pi d squared, which is the big sphere over which the light has essentially spread out, power has spread out. So in other words, the power density at different distances from the sun is simply proportional to the power density on the surface of the sun divided by d squared, which is the distance away from the sun that you're looking at. So it goes as inverse square of the distance, as you would expect, because the energy is getting spread over a sphere. And the surface area of the sphere is 4 pi d squared. So, for example, if you look at the surface of Venus, which is a distance of 108 billion meters away from the sun, you have an irradiance of 2611 watts per meter squared. If you go to the Earth, which is 150 billion meters from the sun, you get somewhat smaller, 1366 watts per meter squared. And if you go to Pluto, which is as far away from the sun as you can get in the solar system, it's about the distance about 6,000 billion meters, and the power density on its surface is very small, less than about a watt per meter squared. So we need to know exactly where you are. So, for example, if you are designing a system for a interplanetary satellite, or exploration or something like that, we need to really be aware of all this. Of course, in addition to this, we have other stars, so there is energy coming from other stars. In that case, you also need to account for that as well. But in this class, we won't deal with that, but I want you to be aware of it. The actual power density also changes as the Earth moves in its elliptical orbit. and the sun's emitted power is not constant. So, of course, the sun has different phases, so you get different amount of energy. But even other than that, the Earth is moving in not a circular orbit, but an elliptical orbit. So some situations, like in early January, you're closest to the sun. When you're in July, you're somewhat farther away from the sun. So you get different irradiance. Of course, the seasons also affect it. Of course, the season is determined by which side of the Earth is pointing to the sun. So that will also change things as well. If you want to do a very, very rigorous calculation of the power density, it can be done with an empirical formula shown here, where N is basically the day of the year, okay, which ranges, of course, from 1 to 3, in this case, 1 to 365. Okay. But for the purposes of this class, of course, we won't go into this level of detail. We will just assume one standard spectrum for designing systems, one standard power, which is about 1,000 watts per meter square, power density. So most of these variations are small for the purpose of designing energy systems. So very standard spectra are used. So there are standards committees around the world which have determined these 3 standard spectra. AM0 refers to air mass 0. We'll see what that means in the next few slides. But it represents the spectrum out in space. So that's the red plot here. Again, this is wavelength, and this is spectral irradiance, watts per meter square per nanometer. AM1.5 direct is the green spectrum here. That represents the direct sunlight on the surface of the Earth, and air mass 1.5. We'll see what that means. Direct represents the light that directly comes in. In other words, it is collimated. It is coming straight from the sun. It is not diffused or scattered by the clouds or anything like that. Whereas blue curve AM1.5 global is direct plus all the light that is scattered from the clouds or from dust particles and things like that. So you can see the energy of the global is higher than the direct. And the difference between global and direct is very important, particularly when we talk about solar concentrators. We'll come back to this. So it is useful to have some physical understanding of why how solar radiation at the Earth's surface is affected by different factors. So let's think about this briefly. While the solar radiation incident on Earth's atmosphere is fairly constant, it primarily changes by small amounts by some changes in the emitted power from the sun and also the distance between the sun and the Earth. The radiation at the Earth's surface can vary by a large amount, clearly from night and day, right? It can go from 0 to 1,000 watts per meter square. Of course, it can also change by atmospheric effects, which includes absorption and scattering. So if you have cloudy days, for example, or it's raining, water vapor, if it's very humid, for example. It can have local variations in the atmosphere, such as water vapor, clouds, pollution, latitude of the location. So which way, are you in the northern hemisphere during winter or during summer? Season of the year and time of the day. So parameters that change, which are important to us, are spectral irradiance, the total power density, and the angle of incidence. And we need to actually be aware of all 3 of these things when we design systems, because typically we want systems that work around the year. Now, atmospheric effects that contribute these changes, there is a reduction in power due to scattering, absorption, and reflection. So if you look at the input light coming in, some of the light is absorbed, which is shown by this red arrow lines on the left. Some of the light is scattered back to space by cloud or dust particles. Some of the light is scattered into Earth. And this forms the scattered or diffuse light coming back to Earth. Okay. Of course, all this can also change the spectral content of the light, because different particles absorb light at different wavelengths. So we know that the sunlight looks different during the morning than it does during noon. Diffuse and indirect component sunlight and local variations in the atmosphere. So approximately 70% of the light that comes in from space enters directly to the Earth, whereas about 18% is absorbed in the atmosphere, 3% is scattered back to space, and about 7% is scattered, diffused into the Earth. Okay, so if you look at the energy total power difference between the AM0 spectrum, which is out in space, and the AM1.5 spectrum, which is down on the Earth, is roughly 77%, which is 70% indirect and 7% scattered or diffused. Okay, so that's a good number to keep in mind. Just a few other notes about atmospheric effects. High absorption at certain wavelengths where photon energies are close to the bond energies of specific gases like ozone, carbon dioxide, water vapor give rise to those very sharp spectral peaks we saw. And those are sometimes problematic depending upon certain kinds of photovoltaic systems we design, concentrator systems. And we'll talk about that later in this class as well. Most of the far infrared, which is greater than 2 microns in wavelength, is absorbed by water and carbon dioxide. Most of the UV, which is less than 300 nanometers in wavelength, is absorbed by ozone, but clearly not enough to prevent sunburn. So that's why we need, and also that's why ozone is an important component. If you lose ozone, as we had in the case of Australia with the big ozone hole, this is when more of the UV passes through, causing sunburn. In any case, all these absorptions cause these very deep troughs in the spectrum, very large changes. The dust and air molecules absorb across the spectrum to reduce overall power. So we know this from experience. When the sun is overhead, all the wavelengths are roughly uniformly absorbed, and the sun looks white, whereas during morning and evening, the optical paths are longer, and the shorter wavelengths are more effectively absorbed and scattered. And this is something we'll talk about later on, but the shorter wavelengths are more effectively absorbed, which means that the longer wavelengths pass through more easily, and the sun looks a little reddish, and the power density is reduced. So this is just a plot showing approximately the energy per unit time. So that's power as a function of the time of the day. Obviously, before the sun rises, it's 0. As it goes up, goes to a maximum and goes down. And this is the plot for the equator. And as you go more north in latitude, the total power goes down. Okay, and this again, obviously, is expected. Now, I just want to emphasize the difference between direct and diffuse light, because this will become important when we talk about solar concentrators. The Rayleigh scattering is basically what's causing diffuse sunlight. And this is basically the fact that the shorter wavelengths are scattered much more than the longer ones, which is the reason why the sky looks blue, because blue wavelengths, bluer light is scattered, and it comes back to our eyes, gets scattered back. So that's why the sky looks blue. If you did not have the scattering, the sky would basically look black, as you know from the moon. If you look at that, there's no moon, doesn't have any atmosphere. You see, the sky looks black because there's no scattering. About 7 to 10% of the light is diffuse on a clear day. Okay, so let's do a quick practical example, thinking about all these concepts that we just talked about. Is the fraction of high energy photons higher in diffuse or in direct sunlight? Okay, so think about diffuse and direct sunlight. Which one has more high energy photons compared to low energy photons? Not flux, but the energy. You guys can think about this for a second before for half a minute or so, and then pick up to the answer.
You said which one has higher energy, right?
Yes, which one has a higher fraction of high energy photons? So essentially, which one has higher power density, assuming everything else being the same? Is it the diffuse or the direct? So So the answer is basically in the fact that when you look at diffuse, it is comprised of the scattered light. And in diffuse sunlight, the short wavelengths are scattered. So they comprise more of the diffuse. Okay? So the diffuse light is bluer than direct light. So the diffuse light really has more high energy photons than direct light. But of course, on an absolute scale, the total power density within diffuse light is much smaller than direct light, right? It's only 7 to 10%. But the fraction of high energy photons is higher in the case of diffuse light. Does that make sense?
It's because the wavelength is shorter than direct.
Because shorter wavelengths are more scattered, and they contribute to the diffuse light more than longer wavelengths.
I have a question for the.
Yeah.
And you said on the around noon is direct light, right? And
Yes.
it has shorter wavelengths. And in the morning they have a longer wavelengths.
It will reach your eye. That's correct. If you directly from the sun, right?
Direct.
Yeah. So think about it this way: the light, if you look at the sun, it's the direct light that reaches your eye. During the noon, if you look up at the sun, it looks white because almost all the wavelengths reach your eye equally. Okay, so it looks white. Whereas during the morning or evening, the shorter wavelengths are scattered away. So you see more of the longer wavelengths, which are not so much scattered. So that's why it looks more reddish. Okay?
Why it's scattered? Is it because the cloud absorb the
Because the atmosphere will scatter light, but it will scatter in a wavelength dependent manner. Short wavelengths are scattered more efficiently than long wavelengths. So one important thing to also realize, and which is actually the answer to our question, is plotted here. So this is the direct sunlight spectrum shown in black. The light curve here is the diffuse sunlight spectrum, and you can clearly see most of the diffuse light is in the shorter wavelengths, even though the energy is smaller. And you can see the human eye response here. And we will talk about the human eye response for lighting applications later on. But you can notice that the peak response of the eye is exactly at the peak of the sunlight. And this obviously comes from evolution. Our human eyes have evolved to essentially match the peak spectral radiance of the sun. It's roughly in the greenish yellow range. Okay, so we talked about the AM as a definition of the standard spectra. Now we need to understand what that means. It refers to air mass. Air mass is the path length which light takes through the atmosphere, normalized to the shortest path possible. That is when the sun is overhead. That's the shortest path. It quantifies the reduction in power as light passes through the air. So you can look at this situation being the reference case, which is the shortest path for the light. This is the atmosphere, that's the Earth. And if you are in this situation, where it passes through here, the light that comes in this situation passes through more of the atmosphere than in this situation. The air mass AM is defined as 1 over cosine theta, where theta is this angle from the normal. So let's think about this for a second. So what is the air mass at noon?
It's 90 degrees cosine of 90 degrees.
No, look at it. When it's noon, it's right here, and theta is not 90, but 0.
Yeah.
Right? So air mass will become 1. Now, what is the air mass at sunrise? And the sun is way down in the horizon. it becomes 90 degrees, like you said. And cosine of 90 degrees is 0. So air mass becomes almost infinite. In other words, light is going through almost an infinite amount of air. But for a standard, we will always assume air mass of 1.5, and that's roughly 30 degrees. And that's a standard which we can use for designing systems. The exact air mass is complicated, and you have to take the curvature of the Earth into account, so this doesn't go to infinity. A more accurate formula is shown here, where you can see when theta goes to 90 degrees, it doesn't go to infinity. It's because of the curvature of the Earth, and that's counted here. And this is, again, just for your information. We will not use it for the purposes of this class. We can also distinguish between the direct component on a plane perpendicular to the sun rays as a function of air mass, shown by here. We also know that the intensity, this intensity, by the way, which is watts per meter squared, which is the spectral power density. It's integrated over all the wavelengths. The intensity, of course, increases with height above sea level because you're getting closer and closer to the sun. So places like Utah and the desert Southwest has higher solar power densities. And we can also account for that with this equation, where h is the height above sea level in kilometers in this particular case. But these variations are relatively small. So we will stick to a very standard AM 1.5 spectrum for the purposes of design. But keep in mind, even on very clear cloudless days, the diffuse component of the sunlight can be up to 10% of the direct, as we said before. So this is something we'll need to keep in mind as we design systems. Okay, so the list of potential projects. So this is basically the end of the basics of solar radiation. And I want to spend the last part of the class talking about potential projects. So like I said at the beginning, I'll assign the class teams and projects in tomorrow's class. But again, these are suggested projects, again, to give you a little bit more input into what are possibilities. I listed a few: solar water desalination, pasteurization, optical classification and sorting of recycled goods, which we haven't talked about, so we'll take a quick look at it. Concentrators and other optics for hybrid photovoltaics or hot water systems. Solar refrigeration, ice making and cooling systems, and solar daylighting systems. So again, this is for all you. Some of you have already responded, but if you haven't, please send me a note with your, I would say, the top project choice. You don't need to give me 3, but just 1 is enough. So at this stage, let me stop for a second. Is Naren there?
Yeah, right there.
So how many students are in the class right now?
There are just 2 of them. So one of them had to leave because he has another class.
Okay, that's fine. So we can stop here because I know you guys have already given me your input.
Yeah, or before we'll talk about, like, I was thinking about the solar tracker, but once we discussed, he was like, we have another idea, like more like a solar cooker or solar concentrator. It's like all kinds of lenses.
Yeah.
So we have multiple lenses around this, like a spherical shape, and have like a container, so more like a solar cooker, but on the top of the material is more